Today, I'm going to walk through the Greenpeace Secure Development Policy. This includes our coding standards, core security principles, and how we use automation and testing to prevent vulnerabilities in both code and system architecture. This policy was created to standardize secure development practices across the team. As development teams grow, it becomes easy for security practices to become inconsistent. This policy ensures that all developers follow the same expectations and guidelines. It also supports a defense in depth strategy, meaning we rely on multiple layers of security instead of just one, reducing the likelihood of a single point of failure. This table summarizes all identified vulnerabilities and ranks them based on severity, likelihood, and overall priority. These rankings are based on how likely each vulnerability is to occur and how severe the impact would be if exploited. For example, SQL injection, buffer overflows, and out-of-bounds access are ranked at the highest level because they are both common and can directly lead to system compromise or data exposure. Lower level risks are still important, but they are less likely to immediately impact the system's security. To identify these vulnerabilities, we use automated security tools throughout development. Static analysis tools like SonarQube and CPP-Check help detect issues early in the coding phase, such as unsafe input handling or memory misuse. Dynamic tools like OAuth Zap simulate real-world attacks, including injection vulnerabilities. Valgrind is used to detect memory-related issues at runtime. These tools allow us to catch and fix vulnerabilities before they even reach production. These are the 10 core security principles that guide all development decisions. They include validating input, following secure design practices, minimizing system complexity, and applying the principle of least privilege. These principles ensure that security is built into the system from the beginning, rather than being added later, which is much less effective. These coding standards are prioritized based on risk level, which includes severity, likelihood, and overall impact. High priority issues include validating input data, safe string handling, and preventing SQL injection, because they can directly lead to data breaches or system compromise. Median risks focus on memory safety issues, such as use after free and pointer misuse, which can cause crashes or unpredictable behavior. Medium-level risks still matter but are less likely to immediately expose the system. For example, input validation should always be applied when handling user or external data, while safe string handling is critical when processing input to prevent buffer overflows. This prioritization helps developers focus on the most critical vulnerabilities first. Encryption protects data in 3 different states. Encryption at rest protects stored data, such as databases or files. Encryption in flight protects data while it's being transmitted over networks, typically using secure protocols like HTTPS. Encryption in use protects data while it is actively being processed in memory. For example, encryption in flight is used when a user logs into a web application, ensuring their credentials are protected during transmission. This ensures sensitive data remains secure even if a system is compromised. The AAA framework controls access to the system. Authentication verifies who the user is. Authorization determines what actions they are allowed to perform. Accounting tracks and logs their activity. For example, authentication is used during user login. Authorization controls access to admin features and accounting logs actions such as database updates or file access. This framework is critical for both security and auditing purposes. Unit testing ensures that the system handles input safely and behaviors as expected under different conditions. This includes testing invalid input, edge cases, and memory safety. Invalid input testing ensures that malicious or incorrect data is rejected. Edge case testing evaluates how the system handles extreme conditions, such as a minimum or maximum values. Memory safety testing ensures proper memory usage, including detection leaks and preventing unsafe user access. For example, unit tests can be used to validate input functions to ensure invalid data does not cause system failures. We apply unit testing using the Visual Studio C++ testing framework, specifically MS-Test. Test methods are created for each function, and assertions such as assert true and assert false are used to verify expected outcomes. These tests are automated during development and run as part of the build process, helping to catch issues early. They can also be integrated into a CI/CD pipeline to ensure code is always validated before deployment. Testing is also expanded to include security scenarios, such as simulating injection attacks, testing malicious input, and stress testing memory. Security is integrated into every stage of the development lifecycle. During development, static analysis tools identify issues early. During testing, automated tools validate functionality and simulate attacks. After deployment, systems are continuously monitored for unusual activity. Tools like SonarQube, CPP Check, and OWASP are used throughout this process. This approach ensures continuous vulnerability detection and supports a strong defense in depth strategy. Addressing vulnerabilities early significantly reduces cost and risk. Waiting to fix issues increases the likelihood of system failures, data breaches, and more expensive remediation later. High-risk vulnerabilities such as SQL injection and buffer overflows should be addressed first because they have the highest impact and likelihood. Lower-risk issues can be handled after critical threats are mitigated. This approach ensures resources are they are needed first. Moving forward, there are still areas that need improvement. As systems grow more complex, new vulnerabilities and attack methods will continue to emerge. Future efforts should focus on expanding automation power, improving security testing, and continuously updating coding standards. Security is not a one-time process. It must evolve alongside new threats. In conclusion, the security policy provides a structured and consistent approach to secure software development. While strong protections are already in place, future improvements should focus on adapting to evolving threats and expanding automated security practices. Following industry standards such as OWASP recommendations will help ensure the system remains secure over time. By continuously improving and maintaining these practices, Greenpeace can reduce risk and maintain a strong security posture.